All right, now we're doing astronomy here, and almost everything we know about our universe, particularly outside of our solar system, comes from light. That's what telescopes, we're astronomers, we use telescopes. What do telescopes pick up? Light. So that's our main tool. The main way we know about the universe out there is by using telescopes to observe it. So first and foremost, we need to know a little bit about light. We need to know, what is light? What is light? When I ask this question in class, people think a little bit, and usually they come up, well, first of all, light is a form of energy, okay? And the other thing people mention is light is a wave. True statement. A wave. Okay, so let's think just a little bit about what waves are. What kind of wave is light? There are many sorts of waves out there. There's sound waves, there are earthquake waves, there are waves in water, ripples in a pond when you throw a stone in there. So what is a wave? Well, okay, let's think about that. A wave is what happens. In order to get a wave, essentially you generally have to have two forces out of balance. So a wave, let's think about that. Two forces out of balance. So, for instance, in a water wave, you throw a stone into the water, and then, the water goes up and down, these wave-like sort of things. Well, gravity pulls the water down, and then water pressure pushes the water back up again. Now, when the water is just flat, those forces are in balance. You introduce a stone that adds energy to the system, and now there are places where gravity wins and the water level goes down, and places where pressure wins and the water level goes up. And so water pressure and gravity push against each other in order to create these waves. So, well, what's going on with light waves? In light waves, the two forces that are out of balance are the electric force and the magnetic force. Two forces out of balance. In this case, we have electric and magnetic. Those are the two forces which are out of balance, which are pushing back and forth on each other. The electric force, that's the force where if you take a balloon, rub it on your head, stick it to the wall, that's the electric force. Static electric force, active electric force in circuits and things like that. And then, of course, the magnetic force, that's the force that holds magnets and pictures to my refrigerator. That's what we're talking about. And initially, when those two forces were studied, they were thought to be totally different forces, and they seemed to talk different languages. A magnet and a charged balloon don't talk to each other. They don't respond, which side of the magnet does the balloon respond to, and it doesn't work like that. However, it was discovered in the 1860s by the wonderful Scottish physicist James Clerk Maxwell. Was studying the equations of electricity and magnetism and found that he could combine these equations together, and if he did, that these things could push back and forth on each other and create electromagnetic waves. Now, when he did this, he thought, well, what a strange thing, electromagnetic waves. I wonder how fast they would travel. And so he calculated purely, he's just doing equations. He's doing pencil and paper. He's in his study. No laboratory stuff at all. He's just doing math. But when he put the mathematics of electricity together with the mathematics of magnetism and discovered, hey, these should allow waves to move, he calculated how fast would these waves go, he calculated it out, and that speed he got was the speed of light. The known speed of light had been measured before, years before then, and so that's how James Clerk Maxwell became the first person in history to know what light is, to know that light is an electromagnetic wave. His theoretical waves, hey, they travel exactly the same speed that we know light waves travel. That's what light is. Light is made of electromagnetic waves. So let's talk a little bit about, okay, waves in general. Measuring waves. Measuring waves. So one thing we can do is we can measure their speed. Speed. All light waves, all electromagnetic waves travel at a speed of 3 times 10 to the 5th kilometers per second. So fast that it takes light only about 1 second to get here from the moon, about 8 minutes for light to get here from the sun. And then, of course, what else can we measure? We can measure the wave length. We can measure this. So if you were to take a wave and you were to freeze it, if you were to just stop moving for an instant, freeze the wave, take out a ruler, measure the distance here from one peak to the next peak. That is the wavelength. We measured that with the Greek letter L. That's a lambda, which is a Greek letter L, so that's the wavelength. It can be measured in meters or centimeters or we can measure it in feet or inches. For light waves, it's often measured in nanometers, which are really small. 1 nanometer is 10 to the minus 9 meter. That's 1/1000th of a meter, but light waves have really short wavelengths. The other thing we can do is we can measure frequency. And so what is that? Well, okay, to get wavelength, you take your wave and you freeze it, and then you measure peak to peak. To get frequency, you stay at one place. So as a wavelength is all measured at one time. If you stay at one place and then you count the number of peaks you receive in every second, that measures frequency. Frequency, we measure in peaks per second. And peaks per second, we, in honor of one of the first people to generate radio waves, we name peaks per second, we call that Hertz. HZ, named after Heinrich Hertz. So a few years after James Clerk Maxwell said, hey, light waves are electromagnetic waves, I wonder if there are other sorts, and then Heinrich Hertz generates some of the very first radio waves. So these are some ways that we can measure waves. And so these allow us to now distinguish between different kinds of light. Okay, so measuring waves, and now we want to do light waves and colors. Light waves and colors. So we ask ourselves, what's the difference between different colors? What makes red or green or yellow or orange or blue different? You know, you can take white light, and if you pass white light through a prism, that prism will spread it out into a spectrum of colors. Red, orange, yellow, green, blue, and violet. So red, orange, yellow, green, blue, and violet. And we find that, okay, that white light is a mixture of all these colors. That was discovered by Isaac Newton, and that you can split white light in this way, or put these colors all back together. His great experiment was he put all the colors back together to turn them into white light again. And we find that the difference between these is in terms of their wavelength. So in terms of wavelength, red has the longest wavelength, the longest wavelength we can see with the eye, and violet has the shortest wavelength that we can see with the eye. All of them travel at the same speed, but they vary from long wavelength over here to short wavelength over there. And since they all travel at the same speed, well, let's see, that also means there's a relationship between wavelength and speed and frequency. So that means the red light is going to have the lowest frequency we can see, frequency, so the smallest number of hertz, and violet light is going to have the highest frequency, the highest frequency we can see, highest frequency we can see with the eye. And then we discover, are there other types of light that we cannot see? And the answer is yes. The visible light is just one type of light. There's this whole electromagnetic spectrum. All these other types of light, these other waves which are identical in every way to light, they just have wavelengths we can't see. So it extends out beyond red and beyond violet. And so let's do the whole, we need to know the whole electromagnetic spectrum. The electromagnetic spectrum. And we find that visible light is just this tiny, tiny little portion in there, and that there's all these other things. So on the long wavelength, low frequency side of the spectrum, the longest possible wavelengths, the lowest possible frequencies, we call these radio waves. And then there are microwaves. Microwaves. And then there's infrared light, infrared. Okay, there is a tiny little bit of visible, so I'll put a little tiny bit in here. So here goes red, orange, yellow, green, blue, violet. On the other side of violet, there's ultraviolet. On the other side of that, there are X-rays, which are just very short frequency light, and then finally gamma rays. Gamma rays. And so this would be the shortest wavelength and the highest frequency. So there's this whole spectrum of these different types of light, really. So I'll talk about infrared light, ultraviolet light. I'd even say, radio waves. Well, what are these? They're the same thing as light. They just have longer wavelengths. So as astronomers, we use this all the way across the spectrum. And then we make another great discovery, and we discover that these waves are composed of photons, of particles of energy. That if you get a light wave, well, it has many of these tiny little particles in it. And when the wave energy is absorbed, say in an individual atom, it either gets a whole photon, or it gets nothing. You can't get half a photon or 3/4 of a photon. So energy is received in packets. It's given off and received in packets of energy, and the energy is proportional to frequency. So this is low photon energy. This is high photon energy. So if I get a beam of red light and a beam of blue light, and those are equally intense, they're giving off the same amount of energy, well, they're transmitting the same amount of energy, that means there must be a lot more photons in the red beam than there are in the blue or the violet beam, because each photon of blue or violet light has more energy than each photon of red light. Now this is interesting. This is interesting because it explains a lot of things. For instance, this explains why gamma rays are dangerous. Why X-rays, if you have, X-rays can give you cancer, because that means even if the intensity is not too much energy is passing through you, those photons pack so much individual punch that if one of those photons hits one of your cells in the right place where it hits your DNA, and it delivers all that energy in one highly intense photon, it can break your DNA, and if it does in the wrong place, it causes you to have cancer. It makes it so that that cell reproduces, never stops. It breaks. If your DNA gets broken in the right place, you can get cancer. On the other hand, it means that if I'm on down here, radio waves, microwaves. I don't know. There was something a few years ago about maybe cell phones causing cancer or power lines overhead causing cancer, and I knew that those are garbage to begin with. There's not a chance that cell phones or power lines can cause cancer. Why? Because those things are emitting radio waves. Radio waves have very low energy photons. That means you may have a lot of them going through you, but in each individual spot, they're delivering these tiny little bits of energy. Not enough energy to break your DNA. Not enough energy to cause cancer in that way. So I knew, oh yeah, whatever, somebody did their statistics wrong. It's not possible for you to get brain cancer from your cell phone, because those radio waves have photons with such low energy that they were not capable of breaking your DNA and then causing the cell to reproduce and cause cancer. On the other hand, you want to know what can cause cancer? Guarantee, sunlight causes cancer. Get up here in the ultraviolet on the other side of the visible. Ordinary sunlight has plenty of ultraviolet rays in it, and that has enough energy to give you sunburn, and then if you hit in the right place, then you can get skin cancer as a result of that, because their photon energy is high enough. But anything below the visible isn't going to have enough energy in each photon to break your DNA apart and cause cancer. So that gives you some insight into this. And then as astronomers, we use the whole spectrum. Right now it's visible and radio waves pretty much get through the atmosphere down to the surface. So if I want to build an X-ray telescope or certain types of infrared telescope, then we got to get up into space, because our atmosphere blocks out all the X-rays that are coming in from space. People talk about Superman having X-ray vision. If Superman had X-ray vision, he would be blind, because there aren't X-rays going around, bouncing around enough. There aren't enough. Our atmosphere blocks out the X-rays from the sun. So that's why we have to send X-ray telescopes and other types of telescopes into space, because there aren't any ones down here. And that's a little bit about the electromagnetic spectrum and what light is.